Hey everyone, we have two short presentations now to round everything off. First of all, we're going to hear from two SFI-IRC pathway program researchers. First, we're going to hear from Dr. Nanasaheb Thorat, who is a principal investigator at the Department of Physics at the University of Limerick, and he's going to talk about plasmonic materials for cancer theranostics. And then we'll hear from astrophysicist Dr. Patrick Kavanagh, who's a PI at the Dublin Institute for Advanced Studies, and he will talk about commissioning the mid-infrared instrument on the James Webb Space Telescope. So if I could invite Nanasaheb up to the stage, that would be great. Thank you.
Thank you so much. Indeed, it is a great pleasure to present something about my recent research. It's not directly related with the SFI project that we just started, but the background research or the previous couple of years, we are working on some cancer theranostics part. Basically, I'm associated with the physics department in Bernal Institute, as well as the Limerick Digital Cancer Research Center, which is newly established in the University of Limerick. Before that, I was working in the University of Oxford and one of the universities in Poland on different projects. So some of the part work I'm going to present today. As you heard from the morning, many physics, one physics lecture and one clinical bio lecture, where they combine the superconductivity, which is equally important for the health sector like MRI and other. And of course, there is a clinical ways for many diseases that is presented by one of the speaker from UCL. I'm just enlightening both things together, so how physics is important for the health sector. All the technologies in the health is dominated by the physics formulas. However, they are mostly money-making business models for health sector. However, physicists are still lagging in that sector. One of the sector now booming after the COVID or before the COVID is the photonics, that is the science of the light. We use the light for many purposes. It may be from visualization to the therapy. So light is very interesting. So it has energy, it has a wave, it has both kind of dual activity we call wave-particle duality. So light interacts with matter, and when it interacts with matter, there is a phenomena. Maybe the light absorbed, scattered, or many other physical phenomena. I'm not going in that. But that interaction gives us some hidden things for the cancer or many other diseases. So how it works? So as we know, the light, which has a big market, which has everywhere on the planet, vital role for our daily lives. And of course, that is the energy source from the sunlight, that is natural. We get food. Most of our 90% body is dominated by the light. And it is a growth for world's economy and huge investment. We are looking after the COVID and recent breakthrough in the photonics. Some of the physics Nobel laureates who discovered some quantum computing. So that might be all associated with the photonics things. It has a big history. Science with the light and technology that is controlling our daily activities and other phenomena. Though we are in 21st century, its history starts from the 17th century when the first Newton who discovered about is it a particle or is it a wave, and then there is two dilemmas about the theories. Well, I'm not. In the future, the light or photonics will dominate the market and will replace most of the electronic stuffs in coming years. We know the light, it has both activities, both duality. It might have a particle, it might have a wave kind of structures. So this is what we use a wave for our in daily stuffs, from mobile to X-ray machines or MRIs, and they all depend on the many phenomena. Well, this is what we are doing. We are mostly working on the light-activated nanomedicines. Why we are working on that? Because, all the evolution theories, they project that there is interaction between the light with water and matter, and then the first human being or maybe living things have evolved from the sea, ocean, or on the soil. So these phenomena are associated with the light because of their interaction with the matter. Light has both duality. So sometimes it is a particle, sometimes it is a wave. If we consider the wave, light is a wave, we can use that phenomena for diagnostic purpose or imaging purpose. So it has a scattering, it may be a non-linear or linear scattering, it has a fluorescence and other phenomena. While if we consider the light as a matter or a particle, we can go into the therapeutics part. So therapy mostly, the discoveries with the light as a interaction with matter, as a particle, it may be a therapy like a photothermal therapy, a photodynamic therapy. There are some chemical reactions between light with some molecules, or in between that we need to bridge some nanomaterials or other materials. We can give us the therapeutics part. So these light matter interactions are actually associated with the absorption phenomena to the fluorescence and scattering as well. Mostly light interact with the water, not as other matter. Well, fluorescence is another phenomena which is associated with the interaction of light with matter and materials that gives us some of the therapeutics part like photothermal therapy, where we can excite some energy, electron, or maybe some photons from one state to another. If there is a energy imbalance, that is what the photothermal. If there is a reactions, that is what the photodynamic therapy. Both therapies are well established in the cancer. What we are looking. So our work is mostly on the cancer. We have focused on two cancers. One is the breast cancer and another is the brain cancer. Brain cancer for two is adult brain cancer and the pediatric brain cancers. We have recently started with the converging the physics with the chemistry and the biology together. So when we talk about the physics, it is meaning the energy. Well, chemistry deals with the reactions and biology all with the phenomena in the living systems. So physics has energies in maybe a magnetic energy, ultrasound energy, electric energy too, and of course the light. So our work is mostly focused on designing the combined strategies, light and magnetic active materials that can be used for diagnosis purpose as well as the therapeutic purpose. So we are working on the materials, especially plasmonic materials and magnetic materials together for light-activated and magnetic-activated therapies, including the magnetic hyperthermia, photothermal therapy, and of course MRI and CT scan. So what form of energy we are dealing? Again, I'm coming with that slide. So light is energy, of course, and electromagnetic radiation. So energy means is photon, and the radiations, it's a wave. So we are mostly on the both ways. So we are using this light for diagnostic purpose, maybe near infrared light, or the visible or UV light for excitation of nanomaterials in different fields. The one of the best example of material science which converts the photonics to the health is the gold, which is very famous material in the research, not only in health but in other sectors as well. So when the light interact with the gold, it may be absorbance. So that absorbance, it changes with respect to their size. So if we can tune the size of the material, maybe we can get the different absorbance for different applications. So gold is used for diagnostic purpose. The recent well-established example is our COVID test, rapid test. They are based on the gold materials. And when the gold is a plasmonic material, there are some materials, they are non-plasmonic, but they can be excited under the light, laser light. These are the hybrid materials. We work on the hybrid materials as well. Recently, there were breakthrough with the fiber optic systems for the excitation of materials inside the tumor for liver or maybe kidney or maybe another tumors which are not accessible from the outside of the body. So some endoscopes were developed. There were targeted photothermal therapy, of course, for animal studies. So they use the light-activated materials, especially a nanoparticle with different size, and we can excite them as a photothermal therapy or maybe a photodynamic therapy together. Some of the materials are being used for exciting brain for different purposes. There are two types of materials. They can be single excitation, double excitations, and mostly single excited gold material is being used. Well, I'll come to our work, what we are developing, what we are doing. This is our recent breakthrough that was awarded the European Commission Radar Prize for excited and interesting therapy based on the photonics and magnetic field for cancer treatment. So we use the breast cancer model there for exciting that with the gold and magnetic materials. As we know, breast cancer is the most dominant cancer in women, very less in men, but it's mostly dominated in the women. And they have more than 10 molecular subtypes and more than 40 type of heterogeneity in a single tumor. So using the current radiotherapy and chemotherapy is not viable for that, as we know. Well, what we have developed a very simple plasmonic cell materials, gold with a magnetic core, and we did some initial light excitation with the photothermal therapy and, of course, the magnetic hyperthermia therapy, that is the magnetic field excited materials. We got the breakthrough with 100% killing cells, not only in the laboratory scale, but in animals too as well. This is what the technology recently we transferred with one of the company from Poland. Also, we are using their interaction for the infectious disease. As we know, after COVID, everyone is curious about the infectious disease. They might be viral or bacterial. One of the major problem after COVID is the drug resistance by bacteria, antibiotic resistance. So we use one of the strain, very dangerous strain, superbug, that is USA 300, which is hospital-acquired bacteria. We developed a nanocapsule which has a gold nanorod with aptamers and other molecules, antibacterial materials. And we use the photothermal therapy to kill the bacteria. We got very good results. Also, within a 30 minutes of time, almost 100% killing of such bacteria. These are deadly bacteria. Well, this is another technology that can be translated to the hospital-acquired infections. This is what work which relates with our SFI project as well. We are developing a plasmonic materials, magnetoplasmonic materials, iron oxide coated with the gold, with the very simple and straightforward chemical synthesis. And of course, there is a bioconjugation with the material because we cannot just use the material alone for any therapy. We need drug and targeting agents. So we use some polymers, drugs, and aptamers for specific targeting to the brain cells. Also, there is a new changes or revolution in the health sector, that is the 3D tumor models or maybe 3D models, bioprinting and other ways are used to develop such a 3D models. The purpose of such models is that even FDA recently announced that you can bypass the animal studies for clinical approvals. However, this is quite difficult because animal studies have very reliable till now. While when we compare the results on animals to the human, only 5% success rate is there. So most of the animal studies fails when we translate them into the human because of the anatomy, physiology, and all the biomolecular structure of tumor in the animal is different than the human. So now most of the oncological companies, they are translating new technologies, 3D tumor models in the lab. We developed one tumor model, which is called the multicellular tumor model for pediatric brain cancer, small children brain cancer, because they are one of the vulnerable patients for cancers. We cannot treat them with the chemotherapy or radiotherapy alone. they may have, we can cure them, but may have some side effects in future, like infertility is the big issue with chemotherapy of child patients. And all these we cannot use the well-established even animal models, which really not feasible for the small children. So we recently developed a 3D tumor model in the lab with different cells, because brain cancer has many consequences. So we use the adult glioblastoma cells, neuroblastoma cells, pediatric neuroblastoma, pediatric glioblastoma cells together. And we use the light-activated nanomaterials to deliver the drug. So we got almost high concentrated localized drug release in this 3D environment and the cell killing. Also, we observed that using the light and, of course, magnetic field, we can deliver the drug or the localized nanoparticle inside the tumor. This is what the results we got with 3D confocal microscopy with some different cells like U87MG, that is adult brain cancer cells, while another two are pediatric cancer cells for brain cancers. Spectroscopic data or the flow cytometry, and of course the confocal or imaging things gives us the hopes that we can target the brain cancer in the lab, 3D brain cancer models in the lab. And our next stage in the SFI project that just we started, that is taking the samples from the patient, developing the tumor model in the lab, and accessing all these chemotherapeutic protocols to give some histopathological report to the doctors how this therapy or chemotherapy or drug therapy will be efficient for patients, especially for pediatric brain cancer patient. And of course, there is a metastasis for brain cancers from breast to brain. So we are working right now on another challenging project, that is the developing some peptide-based cancer vaccines, especially for breast to brain tumors. So this is what our research. We have team across the globe, every corner of the globe, from UL to Poland to Australia and US. We are starting a new collaboration with our SFI project with Harvard Medical School. And of course, we have collaborators from Korea and India as well. So thank you so much for your time and patient listenings. I hope you have enjoyed the presentation. Thank you.
I'll just wait for the slides. Okay, hi everybody. My name is Paddy Kavanagh, and I'm here. First, I'd like to thank the organisers for the invitation to speak at the summit, because I really wasn't expecting it. I'm here to talk to you about commissioning the mid-infrared instrument on the James Webb Space Telescope. So I want to give you a sort of an idea of the work we've been doing in the Dublin Institute for Advanced Studies in DIAS over the last few years in preparation for the commissioning period this summer. What we did over commissioning and how we carry that momentum and expertise forward into the science programme. So I know many of you may not be familiar with the telescope, so I'll just give a quick overview on what's been happening in the last year. So it's the James Webb Space Telescope is the most expensive and powerful telescope ever being launched into space. It cost $10 billion, and it was built by a consortium of agencies, namely NASA, ESA, and the Canadian Space Agency. Now, to give you an idea of the size of it, this thing represents a multi-generational leap forward in observing capability in space. The mirror is 6.5 meters, which means it will probably stretch from here to the ceiling. Okay, it's an infrared telescope, which means you need to keep it cold, and that's what the sail-looking thing is at the bottom. That reduces the temperature on the bottom of the sun shield, we call it, from 80 degrees Celsius to about minus 240. Okay, passively. It'll just reduce it just being there. It's always pointed towards the sun. It was built to answer the biggest unanswered questions in 4 areas of astronomy and astrophysics, and these are the birth of stars and protoplanetary systems, the assembly of galaxies, first light and reionization, and planets are the origins of life. If you think about it, these 4 science teams go to answering or addressing our understanding of ourselves in the universe and how we got to be here, because first light reionization is the first stars and galaxies. Galaxy assembly is how they led to the Milky Way. Birth of stars and protoplanetary systems is how the solar system came to be, and planets are the origins of life is how life evolved in the solar system. Okay, so we've been involved with the James Webb Space Telescope for many years in Ireland. So there's 4 instruments on the back in the science instrument module, 3 of which are near-infrared instruments, but 1 is the mid-infrared instrument, which we call MIRI. And our participation in MIRI has been led in DIAS by Professor Tom Ray. So we're one of the institutes in a European and American consortium who constructed the instrument, worked on calibration and software for the last 15, 20 years, and we also have helped define the science program for the first couple of years of observations. It was launched on Christmas Day, last Christmas Day at about lunchtime, which was a very nervous Christmas Day for us all, because somewhere in the back of your mind, even though Ariane Spas have done this many, many times, you think that thing's going to explode, okay, or crash into the ocean. But it didn't crash into the ocean. It was launched very, very, very successfully. I'll tell you why in a sec. But it was a cloudy day, so it just goes up through the clouds, a tropical storm, it just passed through. About 25 minutes later, a video built by a company in Dublin, a camera built by a company in Dublin attached to the upper stage of the Ariane rocket, filmed the deployment of the telescope into space. Okay, these images were beamed all over the world. They're absolutely iconic, and it was done by an Irish company, which is pretty amazing. When I say the launch was perfect, and this video captures it, but it's in another 5 minutes, I won't play it. They did such a good job on the launch. The only consumable on the observatory was fuel. The launch was so perfect that it didn't need nearly as much fuel to get to where it was going, which doubled the lifetime of the telescope in terms of consumables. There's still questions about whether the instruments can survive that long, but the lifetime went from 10 years to 20 years just with that launch. As you may have noticed, it doesn't look like the big sail and the big mirror when it left the telescope, when it left the upper stage. That's because it had to be folded up to be put into the nose cone of a rocket. It went through 2 weeks of very, very nerve-wracking deployment to be folded out into its final configuration. Just so you know, this involved 344 single-point failures. Okay, so you can see there's lots of little latches detaching and everything being deployed. But if any one of those 344 things goes wrong, that is a $10 billion piece of space junk. Okay, so it was an incredible engineering feat. I'll just let it finish. But it got there. Okay, I'll just click on it out of time. Towards the end of January, it was fully deployed. The final latch locked in on the right part of the mirror, and in the Mission Operations Center, which is in the Space Telescope Science Institute in Baltimore, in Maryland, everybody started cheering. There was still COVID, so there wasn't that many people there. There was still COVID restrictions, so there wasn't that many people there. But we had a functioning telescope. A few months later, after all of the mirrors were aligned and phased up, we got our very first engineering image from the telescope. Okay, and it doesn't really come up great on the screen, but it's just a picture of a boron star. Okay, just to test how sharp the image was, but I don't know if you can see in the background, it's absolutely filled with galaxies. That's because you have that big 6.5 meter mirror collecting loads and loads of light from galaxies in the universe. Every field is a deep field. A week after that, or 2 weeks after that, we had the final optimal focusing of the mirrors. So every instrument on the telescope had the optimal focus, including ours up in the top right there, which is MIRI. So just a little bit more about MIRI, just to kind of give you the idea of what was involved in commissioning. It's not just a camera, it's not just a spectrometer, right? It's a whole suite of different modes in MIRI. There's low-resolution spectroscopy for transit and exoplanet spectroscopy. There's an imager, which is take pictures of the sky in various filters. There's coronagraphs, which detect exoplanets, for example. You block out the light from the whole star and see what's around it. Then you have the medium-resolution spectrometer, which is an advanced type of spectrometer where you take a picture of the sky, but every pixel is a spectrum. Okay, so you get a spectrum at every location in the sky. My work is primarily on the medium resolution spectrometer on the MRS. To commission the instrument in all these modes, you need an incredible group of people, me excluded, I suppose. But this is the MIRI commissioning team. It was one of the great privileges and of my professional career working in this group of people. They're an absolutely wonderful group of people to work with. And back in the spring, we all flew over to Baltimore and set about trying to commission all of these modes. And what does that mean? Well, to be science ready, the instrument has to check off a whole list of properties. So your imager needs to be this astrometrically accurate, your spectrometer needs to have this spectral resolution, and so on and so on. There's a big long list. And we had to go over there and go over there and do this checkout. But we weren't going over blind, okay? We had years and years of ground testing. So this is the science instrument module on the left going into a test chamber. On the right, this is the telescope with the science instruments in the chamber in NASA Johnson, which is where they train the Apollo astronauts to do moonwalks. It's a cryovac chamber. So we had years and years of kind of understanding built up of the instrument, of what we needed to do. But of course, we could never actually shine real stars down into it. We could never shine a real point source into it because you just can't get far enough away from these test chambers to do that. So we used all of this information to kind of develop tools that we thought we would need during commissioning to go through the checklist, make it science ready and release it for science observations. And the first kind of real piece of work we did for this here in Dublin was developing the instrument simulator. Okay, because if you want to prepare your tools for the commissioning run on real data, you obviously don't have any real data, so you just have to simulate it using your understanding of the instrument. And that's what we worked on here in Dublin with colleagues around Europe. We built the simulator, and this is just to give you an idea of how good it ended up. Was that one of these is real and the other is fake. Okay. And the one on the left is the simulated image, and the one on the right is the image we took in commissioning. So you could see our simulator was extremely good. Okay, we had a really good understanding of the instrument. All of the commissioning team used our simulator to create the test data that they used to develop the tools for commissioning. Second thing is the imager geometric distortion, and all that means is that when you take a picture of the sky, the image is distorted because that light has to travel through the telescope and the optical system of the imager and so on. And little imperfections are introduced. And it's kind of, there's a map of it shown on the right there, but we had to measure this and remove it. Okay, and we did a big part of that. We did a significant part of that work here in Dublin. And the final thing is on the MRS. Well, I give 3 examples. We did, worked on lots more, but one of the annoying things about mid-infrared spectroscopy and mid-infrared light is that it interacts very annoyingly, I'm going to use the word annoying a lot, with the detector pixels, okay, because the light will come in and it will actually bounce, it will constructively and destructively interfere and scatter through your detector, so your signal, your real astrophysical signal coming in ends up looking like a big sinusoidal pattern, okay, which is called fringes, right, it's mid-infrared fringing. We developed that, I developed the correction, one of the corrections to remove this from all spectra taken with the MRS. So the first correction has already been, I don't have a laser, sorry, the first correction has already been applied to the bottom, so there's still a lot of fringing in there, and you can see there's a model of a hydroxyline, I think it is, in the green there. You're never going to detect that, okay, but if you can remove that residual fringing, you can suddenly see those spectral features and you can do real science, okay, so this work was led here in Dublin. And all spectra taken with the medium resolution spectrometer are put through these algorithms, okay? So, and obviously if you're going from this kind of contrast, this kind of fringe contrast down to where you can do real science, that's very good for commissioning because you're going to tick off a big box. This is the medium resolution spectrometer team, and I show this because this was taken right at the start of commissioning and we all look so happy and excited to be there, and then the next 3 months happened and we ended up looking like this. Hunched over, exasperated, destroyed, functional zombies in lots of ways. We resorted to this very sophisticated task visualization tool in the top right of Yeah, I'm not going to tell you how close that was to our science readiness review. Okay. But we made our sticky board, and over the next X amount of time, we ticked off one by one all of the different things before going in to present the results of our commissioning run to a very intimidating panel of people, including the director of the Space Telescope Institute and the Nobel Prize winner. But we got there. Okay, we commissioned the telescope. One by one, we commissioned MIRI one by one along the bottom. We checked off all of the science modes, and other instruments did the same. And in the middle of July, the observatory was ready for full science operations, and we started taking the science images, and the first one was released by President Joe Biden on a Sunday night. And that image is the JWST first deep field. Okay, it was the deepest image ever taken of the universe in these wavelengths, and it was done in one night. Okay, it's a phenomenally powerful telescope. Other images were released in the first release, including the planetary nebula at the top left. This is what our solar system would look like in 5 billion years. The top right is a star-forming region, the so-called cosmic cliffs in Carina. The bottom left is galaxies interacting, so it's these kind of mergers and interactions that would have led to the Milky Way, and the deep field in the bottom right, the first deep field. Ever since, we've had more and more amazing images every week, it seems, these days. This is the cosmic cliffs. I don't know if anyone remembers them. They were a famous Hubble image. But this is showing the power of JWST, because Hubble simply can't see into that gas and dust where stars form. And I don't know if you can see, I'm sorry, I don't have a laser, but in the densest regions up along the right, you can see little red stars sticking out. They are baby suns in solar systems forming in these pillars. Okay, so it's pretty amazing. If you could zoom in on one of those stars, it would look something like this, where you have a very young protostar blowing a cavity into the interstellar medium. But I don't know if you can see, there's a very thin black line across the middle. You're looking at this system edge on, and that's the accretion disk of the star. It's in there that planets like ours would form. Okay, so we're really seeing things that had never been seen before. Well, accretion disks have been seen before, but this is the first time we're able to look deep into the heart of where a protostar is forming, because we have something like JWST. We've also had a look at some of the solar system planets, including Jupiter and Neptune, a beautiful image of Neptune, but also exoplanets. The JWST has already imaged exoplanets, and that's just a start. It can also take spectra of exoplanet atmospheres to see what's in them. The zoomed out version of Neptune looks like this. It looks like a glowing pearl in the middle of a field, and again, I apologize, you can't really see it on the screen, but it's filled with galaxies, and I think this holds the record of the picture with the nearest thing, something that's very near in our solar system, but also something that's billions of light years away. The telescope has an amazing dynamic range. So you can see Neptune, Triton is the star above it, and all of this field of galaxies. But the last thing, and I'll leave it with this because I'm out of time, is the most recent deep field, okay? Because now the telescope has had a bit of time to work properly. This is an image taken with the Hubble Space Telescope of a galaxy cluster called Able 2744. And last week, or the week before, we got this update. And again, you can't see it on the screen, but there are thousands of galaxies in that image, okay? Oh, sorry. There, sorry. Oh yeah, it's better up there, yeah. So you can really see the potential and power. And now, not just ourselves and DIAS, I mean, we're involved in, right now, and as part of the Pathway Fellowship, we're going to be investigating supernovae and star formation with the telescope. But it's not just ourselves and DIAS. There's astronomers and astrophysicists all over Ireland in the various institutes and universities who also have access to some JWST time. I'm so excited to see what comes out of it from Irish researchers in the next years. So that's it. Thank you very much.